Welcome to Duke's Finding I&I webinar. We appreciate you taking the time this afternoon out of your busy schedules to join us today. I head up marketing at Duke's, and today I'm honored to introduce our speaker, Mike Ping. Mike is a technical manager at Duke's and has over 23 years of extensive experience in the wastewater industry. He's a licensed professional engineer in North and South Carolina, graduated from Clemson with a degree in electrical engineering. Mike is married with 5 kids, all under the age of 17. And he did want me to share with you that he's 51, and with 5 kids, he's very, very tired. Mike is going to explore cost-effective strategies to detect I&I and help prioritize and locate sources of unexpected SSOs or sanitary sewer overflows. Throughout the presentation, we encourage you to submit questions using the Q&A feature throughout the session. We'll address these at the end of Mike's presentation, and that'll provide you with an opportunity to gain insights and clarifications on the topics he's discussing. If time permits, we'll also provide an opportunity for you to ask a question live. And to do that, you would need to raise your hand and we'll unmute your mic. Thanks again for joining us today, and please join me in welcoming Mike Ping. Thanks, Mike.
Thank you. Only one small correction there. My oldest is 16, not 17.
Well, I said under 17. So.
Okay, sorry. Sorry for that. Well, thank you for the nice introduction, and happy to be here, and thank you everyone for joining. So this presentation is about 30 minutes, so it's not quite an hour. And then, as Mark mentioned, we'll answer any submitted questions and potentially open up the phone line for any kind of audio or verbal questions. So I'm just going to jump right in. The basics here, what we're talking about, it's RDII, or rain-derived inflow and infiltration, generally referred to as quote I&I, and then breaking that down further, there's both inflow and infiltration separately, where inflow generally refers to a direct source of rainwater entering the sewer system, and infiltration is an indirect, and for the most part, groundwater entering the sewer collection system via cracked pipes, lateral connections, cracks in manholes, infinite different possibilities there. This slide is just to sort of note that there are certainly financial impacts to I&I, wastewater treatment plant costs, extra chemicals, extra capacity, extra wear and tear. SSOs, or sanitary sewer overflows, and any kind of unwanted attention on that front. Energy cost in pumping extra water, and then oversized wastewater treatment plant and all the collection system infrastructure, larger pumps, larger pipes. And then last but not least, hopefully not for anyone on this call, but I&I can max out a system and then therefore potentially limit any future economic development, which of course nobody wants to be a part of that, but it certainly is around. So the general approach to locating I&I, I've kind of boiled it down into these 3 general steps. Number 1 being more of an acknowledgement that rarely and really never there's enough budget to locate and remedy all of the I&I. So therefore, the general approach is to isolate a larger area into smaller areas, and then determine which of those areas warrant the limited resources, and then deciphering which amounts could be applied into which of those areas. And then number 3, the data density, as I'm calling it. And if you could just look over at the map on the left, that's for an upcoming flow study where each of the basins or each of the little sub areas are in different colors, but you can see there are 6 black squares. So the density that I'm referring to would be, if there was a different budget or a desire to drill down further, there's no reason that instead of having these 6, it could be 12, it could be 18, but that 18 is, probably going to close to triple triple the budget, or it could just be 2 if the budget's limited. So budget is certainly a big part of this. And then, the overall strategy, the technology, and mapping characteristics, and then other factors, but those are certainly the main ones. So the established industry approaches, I've broken this down into 5, and we're going to focus on 1, 2, and 3 here. So area velocity refers to open channel or gravity flow metering, and then lift stations or pump stations. If they're there, a great spot to collect data. And then level only, we'll touch on a couple of things there. So jumping right into it here. This is kind of the basics of open channel gravity or area velocity flow metering. There's lots of kind of industry terminology kind of being used there, but what we're talking about, looking at the diagram over on the left, it's measuring the flow flowing through the sewer, and the access point it's always well, for the most part, it's a manhole, and you can see that there's a logger and a sensor, and they're connected via a wire. And then not shown, but kind of with the arrow at the top, would be data to a cloud. Now, these days, probably as of the past 10, 12 years, most of the uh, hardware available in the marketplace right now has a built-in cellular modem. So they're pushing data to the cloud almost in real time. And then over on the right, you can see a typical setup where there's a logger. This particular one is manufactured by a company called Hot Company, and we as Dukes, we own several different platforms. We certainly use this one, and you can see the loggers, the dark gray, the biggest of the devices there, and then on the left, that's what's called a FLODAR sensor. It's an area velocity type sensor that sits up above the flow. And then the little blue one is a workhorse for us and for the industry as a whole. It's what's called a submerged area velocity sensor. It does although it looks very different, it does the exact same thing. And then the other 2 sensors here are ultrasonic. So they're used to measure level only, and they typically are used to augment or just add on a redundant level measurement. So there's multiple sensor types. The controller is DC powered. It's out in the system, so there's no AC power being run to it. And that's kind of what a typical setup looks like. To touch on how these things work from a mathematical perspective, you can see the sensors in the red circle there. So this diagram over on the right represents sewer flow, and really there's only 2 measurements happening. There's the area, which is calculated based on the sensor measuring the sewer level, and then the programming with the pipe diameter. Now, it could be a rectangular channel, and that's possible to program those into any commercially available meter. So, but at the end of the day, the area, this cross-sectional kind of half of a circle, has to be calculated. If it's a full pipe, it's fine. It could be surcharged. The system could be overflowing. It's still going to measure the flow. So the level gets measured, and then independently the velocity gets measured. And the way that the math works out, it generates a volumetric flow, such as gallons per minute, MGD, and so forth. So closer look at kind of what a diagram of what this could look like. Just again, that's a submerged area velocity sensor, and it's measuring the open channel flow there. A couple of real life pictures beginning over on the right. You can see this is I think this was an 18-inch pipe. Now, typically, 90-degree bends in the sewer are not a great spot to measure flow, but sometimes it's necessary to just do the best that you can. Its sewer system is not a laboratory setting, so this is one such event like that. So you can see the sensor. If you look closely, you can kind of see there's a little blue haze there. That's the submerged area velocity sensor, and it's mounted to this metal band, which that metal band is not fastened in. It compresses on smaller diameter pipe. It compresses, and the field guide just inserts it as far up into the sewer pipe as he can reach. Generally, it's about a foot. This one's not that far. And on larger pipe, there's a scissor band. There's different sets of hardware to keep the band in place. And then looking at the picture on the left, you can see a little gray, it looks like a hockey puck. That's the antenna. So I mentioned the cellular modem. So this is the same manhole. That's a good example of just a real life application. So from there, the data gets generated and pushed. As I mentioned, it's an almost real time. So it's online data 24/7. The update frequency is part of the programming. So, there's other variables that play into that. It's generally speaking at Dukes, we program these guys to push data every 3 or 6 hours just to conserve batteries, but it can be programmed to push them every 10 minutes. But that's just a screenshot of what flow data looks like. I called out some of the other data just so it's kind of clear. But if you take a hard glance at this graph here, you can see 3 spikes, and those spikes are what I looks like on a flow meter due to rain events. I didn't overlay the rain just to try to keep it as clear as possible. So we'll look closer at these. And so these 2 graphs, so the one on the top is the same one, and the one on the bottom is from the same study, and it was only like maybe 500 or 700 feet away, but on a different sewer line. So the timestamp you can kind of see in gray below the line here, same timestamp. So it's pretty clear. This is actually very clear that the flow meter with the data on the top, huge reaction, right? And on the bottom, there's absolutely no reaction whatsoever. So that graph on the top there, that spike, just the 3rd spike, represents an extra 300,000 gallons. And obviously the graph on the bottom associated with another flow meter represents 0. And here's another just side note. Note the nature of the quick response here, where rain event happens, and all 3 of them have this immediate jump, which generally is attributed to inflow. So this is where these came from on the map here. So you can see the top graph is over here where I have the red 2. The bottom graph is this red 1. You can see that it's on this same pipe. It's actually up here at this yellow star. And flow meter 2 was in this manhole, but the sensor was up in this influent side pipe. So that's just kind of what it looks like. So we're talking about point number 2 on the opening slide deck there. You saw, the idea is to isolate an area further down into its components, to pinpoint and apply resources where it's going to be most effective. So on a basic level, 300,000 extra gallons from this area coming in from the top, and none from the left. And these 2 areas were about in total had about the same amount of pipe in each one. And just another map. That's the same area. So I zoomed it in. I realized the green area looks like it's smaller, but it goes way off to the left pretty far, and way off into the bottom direction off to the right pretty far. But these flow meters were down in this area, kind of where my cursor is, and again, the idea is very basic. It's, hey, this area had a huge reaction, this area had no reaction, so we move forward. These photos are from that same area. So this is from the area that produced that extra 300,000 gallons. And so you can see here muddy water at the top. Quite often, and I would say most times, when you're looking live at I&I, the water's clear. And that's usually a telltale sign in itself, where it's like, the sewer water generally isn't clear, and all of a sudden it shows up and you have a bunch of clear water. Right, it shows up, and you know that it's I&I. This is muddy water, and the utility here that sent this over to us. I mean, they got the project results and decided they had another rain event. We're like, hey, let's just kind of walk out in an easement area off road and, just saw this live, right? So you remember the graph straight up, it also came straight down. So if they weren't out there during the rain event, they would never see this. So just kind of the end part of that story there. You can see the manholes are submerged. There's a manhole here in this second picture, but produced a lot of additional sewer flow. So some general characteristics for sewer flow monitoring. I mean, number one is applications can be very challenging. I mean, this is a real life scene. That's our field tech here. His name is Lucas, and he's installed many hundreds of flow meters, but he has to carry around the laptop. There's a program. He's got the equipment. Of course, when you're on site, kind of like when we started this webinar, we practice it, and then when it's go time, things are different, right? So very same thought process with flow metering. It's a busy scene. He's got a generator here, a blower, gas monitor, tripod, and he's next to a 4-lane road with construction going on. Now, quite often these we could be installing a meter out in the road. So, more risk, just a busier and more challenging environment. So number two would be ownership versus service. Being in the industry, what I've seen with my own eyes, rarely does ownership work for a utility that I've seen. Now, there certainly are exceptions, but it takes a big commitment. Most of the time, again, this is my personal experience, that this data gets generated by a service provider. So number three here, just to touch on the cost, flow data is a relative high cost. We'll talk about level data. That data costs less, and a lot of that is around the confined space and the requirements for installation and confined space entry requirements for maintenance, of which there could be a lot. So there are those things to consider. There are, there's a website that's running. There's data watching by, us, in our case, it's licensed engineers. But these things don't run on their own, and people have to be watching the data, qualified people. And then there's alarming programming that can take place if somebody would like. So, another step in this is, hey, we're going to do a study, or we're going to own and buy equipment, is determining how long to leave the equipment in one location. So we do, in my experience, has been doing a lot of 3 to 6 month studies where the goal was to characterize the wet weather impacts, doing what we just kind of looked at with the graphs. Sometimes they're 12-month studies where the general idea is that, hey, we also want to see the groundwater infiltration, which will show up during dry weather at one part of the year versus dry weather at another part of the year. So the flows could be very different, and generally those are tied to groundwater infiltration values. And then what I'm calling semi-permanent, in parentheses here, sewers, as we all know, are not static system. There's ever-changing conditions, so forth. There certainly are a lot of 2, 3, 4, 5 year service contracts where the equipment stays in one spot for many years. And then the last point here, billing from one utility to the next, where one utility owns the wastewater treatment system, one just owns a collection system, and they have an agreement there to transfer the wastewater. So in that case, I've been a part in my career of what I term as I&I finger pointing, which is one utility thinks it's coming from the other, and you got that going on. So third party kind of finger pointing is part of it. So that kind of wraps up the open channel flow measurement, and we'll kind of shift gears and get into lift stations. So lift stations are certainly an excellent place to within a system, assuming that there are lift stations. ran across a few that there's one in Virginia that I can remember. There's, they have 0 lift stations. Like their system is built where the wastewater treatment's at the lowest elevation, and every single pipe can get there without a pump. So, but that's very unusual. So, lift stations are a great way to segment out a collection system and gather data. So we'll talk about that here for a minute. So yeah, most utilities have lift stations. However, many do not. Many that I've worked with do not know the flow values. There are instruments that can produce that, namely an electromagnetic flow meter. You know, it's actually pretty uncommon. So, most utilities are getting some kind of data out, but they don't know the flow value. They may know that the pumps run 30% longer during X rain event, but they no idea what the flow values are. So the data coming out of a lift station or pump station comes in all shapes and sizes. I've got on the top left, that's called a circular chart recorder that was used in our industry for many years. So it's just it divides it up into days, or it could be a week chart, or it could be a month long chart. But look, at the end of the day, that paper chart comes out and goes into somebody's drawer, and that drawer is probably full of them, and then nobody ever looks at them. And if any historical data needs to be known, then it would be necessary to get all these paper pieces out of the drawer. So I have the little diagram here with paper pencil. There's still a good bit of that going on, where a technician rides out and monitors and writes things down, and then a little clip from Excel here where there's a little bit of computer entry. And just kind of on a tangent, as we all know, in most instances, there's not enough of these guys around at the utility. The utility guys are having to wear lots of different hats and reacting and stretch thin these days. And so that kind of compounds the equation there. Another very common characteristic is that there is a data collection system or a SCADA system, but the information is controlled by an IT department. So I'm sure there's somebody on this call that has this scenario, and it comes in all different flavors. It could be extreme, where the sewer guys just don't have practical access to the data, or it could be that they do, but it's so cumbersome and complicated that they just choose not to do it. But the intentions are good. It's all based around security, but that's certainly a common characteristic. And then then you get into the equation of, like, would it be better to own this type of equipment or let it be provided by a service provider? Look, there's the different things work for different people. So there's if you go the route with boxes showing up, there's installation. Now that could be subbed out to yet another group. There's maintenance, on-call maintenance. There's web service. There's data watching, kind of like the flow meters. So, it's unless there are people standing around with nothing to do, this quite often is not. It doesn't work. There's the kind of this story here where the boxes show up, and year 0, when everything is new, out to year 1, everything is great. Then you get further out, year 2, 3. Look, at the end of the day, it requires a lot of bandwidth, a lot of dedication, stable staffing, buy-in from key people, and some knowledge and so forth. So to touch on, what we do as Dukes, for this kind of segment of the industry, we offer a turnkey service. So we have a box here. We'll take a closer look at it, but the general idea is we're skipping straight to the results. So we offer a turnkey service. It's online in about 30 days. It's maintained with all sensors, all of the alarming programming, which we'll look at, help with the data and so forth. And then on the client side, There's no software. It's as simple as, it's all web based, like any other kind of web based programming, where just general access. If the computer can access google.com, then it can access the data. So a couple of clips here. The web browser in this case is dynamic, meaning if you were to pull it up and leave it on, you could watch the wet well go up. You could see the pumps turn on with another icon and see it go down, and just hopefully just cycle back and forth and not do anything out of hand there. And then there's a mobile device viewing tool, so it's friendly for phones and tablets. So an important part of all of this is what I'm going to highlight up here in red is the right amount of information needs to get to the right people. And in my opinion, no more and no less. You certainly don't want less. Like if there's some kind of alarm condition or critical condition, obviously somebody needs to know about it. But also it generally doesn't help to get too much information where an operator's getting 25 notifications a day, and after a week or whatever, that guy starts to ignore it. So that's not an ideal scenario either. So this platform in this case has a very logic and sequence based alarming, and it can be custom programmed where, again, this is something that we would help with, and we do help with, where the right people get the right amount of information. So look, this is one example, kind of the 1 through 5. So there's 3 levels of alarm, there's a notification, or as I like to say, an FYI. There's an alarm condition, and then a critical condition, right? So it could be that something happens, let's say a wet well that generally cycles from 3 to 6 feet. The operator wants to know, hey, did it go to 7 feet? It's not an alarm, but it's like, hey, just let me know which ones are kind of out of bounds. That'd just be a notification to the operator. At that point, he can pull out his phone, acknowledge it. But if he does not, and it doesn't have to be programmed like this, but it can be, it could be such that if there's no acknowledgement, a text message goes to the supervisor, and then if he doesn't acknowledge it, it goes kind of down the chain. And if there's some sort of super critical condition going on, nobody's acknowledging anything, it could go to like the director. And then all alarm, and this is a screenshot of the alarm history here. All the alarm history is recorded from the very beginning, very easily accessed with a couple of clicks. Pull up the site, click on the alarm tab over there, and boom, there it is. So it's a critical piece to it, and to any of this telemetry is alarming, even the flow monitoring. So just a closer look at the inside of a box. There's not a bunch to look at here, except some, what I phrase, kind of slices of I/O, and some power, battery, and then there's the cell modem. We utilize a cell modem that utilizes 2 carriers. If anybody remembers, just a couple of months ago, the Verizon network went out. So I don't know that anybody had planned on that. I don't think they did, but just to point out, this modem has 2 carriers. So we utilize Verizon as a primary and AT&T as a backup. Just, sometimes they go out for shorter periods, and we just want to make sure it's very robust. But all of the peripheral equipment is included here, the stuff listed, and we'll take a little bit closer look at what all of the parameters those record. So just to point out here that again, to stress on the general idea, all of this stuff to the bottom right of this dash line, that's to be provided as a service. There's no hardware selling going on, where the client can just log in, see the data, do what needs to be done, right? So it just takes it out of the hands there. There's a picture of a pressure transducer here and a generator, but the data that we're recording here, kind of the heavy hitters, would be, of course, the wet well level, the force main, the discharge of the pumps, the force main pressure, the status of the generator, the status of the power grid, the flow rate, which I'd mentioned, like flow rate is kind of uncommon. This works on the same principle as a drawdown. So we've got the influent gallon per minute, the pump motor current in units of amps. So not only are we measuring if the pump is on and off and when it's on and off and how long does it run, but we're actually measuring the current values because they don't stay steady. And that's a key thing for, if you have in-house pump expertise, or if you have a local engineer that helps, analyze pumps or design pump stations, like that's very key information to help troubleshoot and size pumps in the future and just understand what's going on. So we have run times, of course. On the electrical side, because we're collecting the necessary information, we calculate the wire horsepower. On the discharge side, we calculate the water horsepower, rain, and then I put et cetera, because really at the end of the day, this box could be wired up to a light switch and just, hey, when's the light turning on and off? It can be wired up to anything. Now we focus on the wastewater collection system market, but there's nothing to prevent this box from being installed on a water tower. In fact, it'd be a lot easier. Okay, so that wraps up the discussion around collecting data at lift stations. And so we'll talk a little bit about level only measurement. So some general notes on level measurement. Generally speaking, it's kind of broken into two kind of subcategories. One would be alerting, and the second would be some sort of analysis where multiple devices are installed and there's some sort of analysis about the sewer system characteristics, and notably I&I locating. Number two is very important. Generally, the level instruments are built around the idea that you're avoiding confined space entry, which severely impacts pricing, right? When you're installing things topside, it's generally a lot quicker. There's much less risk, and all that translates into a different cost structure. So, but number three, there's still, just like the other two that we talked about, the discussion around ownership of hardware versus a service. So, some utilities I've seen are successful with ownership, but generally speaking, the majority choose to put this out to a service provider. Another aspect would be, generally this equipment can be there's a choice between having cellular based equipment, which you get involved with antennas and data watching, or it could be a low cost manual setup where the data is just recorded manually. Nobody can see it, and that hardware has to be removed and downloaded in order to get to the data. There's the idea, number 5 here, of longer term trending versus short term studies. Short term usually is centered around an I&I detection program of some sort, and longer term could be that, but it could also be, hey, I'm just looking at the standard level during dry weather, and if it's gradually increasing over a 2-year period, let's say, where it could indicate potentially like debris downstream in the sewer pipe. And then number 6 is just to point out that alerting and trending is most of what's going on here. So I mentioned that there's two, so we'll talk about, just for a few minutes here, the analysis portion of level only for I&I. So what we offer at Duke's here is, we frame it as, or we call it micro detection, and we I got it noted at the top. We call it street level I&I detection because it's very dense. So to note the project size, now I'm stating here 20,000 feet to 100,000 feet. That's kind of been the center part of the bell curve from just what we've done in the past. But we've certainly done plenty that are less than 20,000 feet, and certainly done, some that are well over 100,000 feet. But generally speaking, where this fits in the discussion of I&I is like, this is a map clip of Tulsa. Just that's where I was recently, and you're typically, the idea is like, you've already eliminated and have an idea of where you want to concentrate some resources, and generally that's kind of where micro detection fits in. So a map clip here, and just to show kind of the general approach, the study area when we do micro detection is broken up into, I'm stating 1,200 feet micro areas. Look, these are sometimes 800 feet and sometimes they're 1,600 feet, but they're very small, especially compared with flow metering, open channel, or, the pump station setups and SCADA and so forth. The general idea for micro detection for us is to, at the end of the day, categorize each of the smaller 1,200-foot sections into one of four choices: severe, moderate, fair, and good. So it's a quick snapshot just to, hey, is it over here or is it over there? And the it is I and I. So is the I and I over here or is it over there? And then we do provide number 4 here, the volumetric flow estimates. But again, it's the intention behind it is not to carry the flow volumes out to 10 significant digits. It's to say, hey, most of it's over here. This severe area is very heavy, and this one over here is not. So we'll look at what the hardware and a kind of a normal setup would look like. You can see this device. It's an ultrasonic level transducer. We have lots of different, hardware setups. At the end of the day, our goal is to get it to look like it looks over here on this photo on the right, where we're monitoring the flow in the 6 o'clock pipe or the effluent pipe in the manhole, right? And we're recording it every 15 minutes. For in this case, for micro detection, it's a manual measurement. So it's installed, it sits in the manhole, there's no cellular data. So that's what it kind of looks like. So the project workflow is that it's quick. So we install the hardware. There's a 60-day data collection period. Also with rain. Now I realize there's probably some folks on the call on the West Coast or in the more arid climates. 60 days, I would say, is kind of what we mostly do. But for people in more arid climates, certainly more attention has to be given towards, like, when the rain is likely to occur, what time of the year. And we've set up plenty of these in 90 and 120 days and have some contingencies built in for the case of when it does not rain. So in most of the instances, it's 60 days. The hardware gets removed. It gets physically sent back to our headquarters and downloaded. All the data is in a file. It comes into my group. We do the analysis, the delivery, and usually, more times than not, the whole cycle from notice to proceed to report in hand is about 120 days. So it can be very quick. Just to touch on the general methodology here, not to get all into the weeds, but the basic idea, very similar to the flow discussion we were talking about earlier. We're identifying the dry weather characteristics, what the levels were, what's happening during dry weather. We're looking at, of course, what's happening during wet weather, how much, what changed, where did it change. And then we determine the differences in each zone. And when I say zone, I mean the 1,200-foot zone, right? So we take all of that data, we dump it into a big calculator. Now, I have human being put there just because, like, if you've ever been around sewer data, it's not all perfect. Okay, so we feel strongly that a set of eyes still has to look at it and look at the data and so forth. And then at the end, we rank each zone. Now, if there are any engineers that they're on the call or people that have been around flow studies, that it's common to get the question, like, what do we do about velocity? As we're giving out volumetric numbers. So we do take a velocity measurement when we install the equipment originally. And then we do a balance of the flows under dry weather and a balance under wet weather. And just with all the calculations and experience, we feel very confident that about the results. So looking at results on just a map. Now this one is very busy. And I kind of zoomed in. We produce GIS maps with all of our services. So if somebody wants to print a big roll up map, put on the conference table to have a discussion, we provide that. So this is a clip from that, and you can see it's busy with colors. So we stick with kind of the industry standard. Red is the most severe, orange is the moderate, yellow is fair, and green is good, right? So we touched on just the basic idea over here, not over there, right? This is just from a map perspective, that's kind of what it looks like. So in that little circle there, we'll kind of dial in and look at one area just in particular and just kind of touch on it. So first off, this area, it's the furthest upstream, right? And it's severe. And there's probably a little bit more than 1,200 feet, right? So it's got I said it's all the way upstream. Part of it is influenced by the left side, but like, you can see the graph again. I focused this in just so we could see it pretty clear, but um, we'll take a closer look at what that looks like. So dialing in to the graph there, that's from that particular area. So there's two graphs here. The one on the top is level. The one on the bottom is the estimated flow values. On the top, the red is the level. So that's just the level of the sewer. And the blue is the rain. So it's inverted. So you can see what's on the y-axis over here on the right. Zero rain, it's at the top, and when it rains, it comes down vertically. So you can see this rain event here, kind of the January 9th rain event, and you can see one over here. It looks like it's on Christmas. So this is on the East Coast because we do a bunch of studies, and Christmas popped up on lots of different studies. But kind of like we've been harping on since the beginning here, rain. You see the reaction, but this is just an example of what it looks like. Then part of the deliverable package, a report. This is just one clip. We here at Dukes, we make a very concerted effort to make things very simple and understandable. We do provide data, lots of data in the background, but we're just trying to make a concerted effort to make the results in a plain and understandable method where it doesn't take a month to read through the report and understand what's going on. So digging into the data table, this was from a report. So you can see the colors, the asset IDs are from the utility. It's the manhole number, pipe diameter, min, max depth, the normal type of data here that you would expect here, how much time it's spent in surcharge. The ADWF is the average dry weather flow rate. That's an estimated value. The groundwater infiltration, an estimated value there. That's just for this exercise. It's a midnight to 5 a.m. value. And then working your way all the way over to the right, the final calculation is the amount of INI for that specific area in units of how many gallons per day for that area per inch mile of pipe. So it's a little bit like a concentration of INI. And you can see here the more severe have much larger values than if you get over here on the right down kind of in the green, the good area. But that's just a snip of what it looks like. In our case, we have an online portal to access all of this data. It's the same data. It's just accessed electronically. So it's dynamic and click on the map and so forth. All right, that covers the analysis part for INI on level only. And so we're getting kind of nearing the end here. We'll touch on alerting, just a simple alerting system that's level only based. So this is our Duke Sewer Alert service, just kind of an overview of what it looks like. So the key part of this is that the measurement begins at the bench. The idea at Dukes for us is these systems have got to be reliable. The reliability is everything. False alarms because of echoes and whatever's going on as far as the measurement, is a killer, right? So if we've got this set up to where reliability is paramount, but what we sacrifice in doing that is we don't know if the sewer is, I'm going to say 1.1 inches versus 1.2. nor does anybody care for this. This is built to be an alerting system to say, hey, we're only going to begin measurement at the bench, right? And then as it goes up, it'll measure the level all the way until when it's an overflow. The other big feature to this is the sewer can still be maintained. So operators can run a jetter through this and jet all day long, right? This is in a protected housing for just that purpose. Sitting behind the hardware, a very sophisticated software set. I call this kind of the iPhone generation data, and it's a nice look and feel as far as the data is concerned. This is a snip from a graph here. This represents about a month's worth of data. And of course, I picked one out that's seeing surcharge. In this case, this is in units of inches. You can see over 70, this is about 6 feet, right? Not an overflow, but maybe something for the utility that has this to know, right? So some stuff going on. And look, this could be, we're talking about I&I, but for alerting purposes, it can be when like, hey, it's a beautiful day outside, and yet I'm getting alarms. It could be an O&M issue, right? So it's not all I&I. But again, just to stress reliability for alerting. Reliability is everything. No pops, no drops. And just to kind of throw it out there on that sewer alert, stormwater alert, that's my homemade graphic over there on the right. But stormwater is becoming is a growing kind of sector of water and sewer, and so this service can certainly be applied in that area. And to sort of wrap this up, there's no perfect tool in the toolbox. Usually problems require multiple tools. And we focused on these 3 areas: the gravity system, flow monitoring, lift station, data mining, monitoring, and then the level only. There's nothing to prevent, and I would say in most cases it's required some sort of mixing and matching. No 2 systems are the same, so it's usually a discussion, needs to be a discussion, and to formulate a plan for kind of for the best approach. So with that, that's all we have here. We'll get into questions if there are any, but to point out, this is my personal contact information. If anybody, if you want to write it down, you want to have a little bit more in-depth discussion, happy to facilitate. You could even send a text message and we'll set up a time or an email. So with that said, thank you, everybody. I'll turn it, Mark, over to you.
Yes, thanks, Mike. Really appreciate you going through this this topic with a lot of different tools in that toolbox. Let me address some of the questions that were submitted. And so I'll start off with, what about dry weather exfiltration? All this hype about septic tanks polluting the rivers and wells. Maybe it's the leaking public systems. With so much I&I, we need more research on dry weather exfiltration for TNP discharges.
Yeah, so that's something that's come up in conversation. I don't I haven't done to be transparent, I haven't done a study on it myself. You know, groundwater infiltration is a tougher parameter to gather than inflow. So I think exfiltration would kind of fall in line with that, would be my opinion. But that's something that I haven't seen a lot of that, other than just kind of just a little bit of conversation come up. I haven't seen any studies come out that are targeting exfiltration. So that's probably not a great answer for that. And that may be one, if you want to hit me up, we could maybe talk a little bit deeper about it if you'd like to.
Okay. I've got a couple of more, but I do want to address one common question or request that's being made, which is, can I get a copy of the video presentation to share internally? The answer to that is yes. We will follow up for those attendees and give them both options. Mike, a few other questions is what's considered excessive I&I?
Yeah. So look, most of my career, I'm sure people are from all parts of the country. You can pick up that I'm from the South. Most of my career has been on studies involved like Virginia, North, South Carolina, Georgia, Tennessee, maybe some of Florida. So yeah, that's an interesting thing. And like, for me, there's kind of one thing, and then you get out to other parts of the country, and it's exactly that. Like, it's different for everybody. So I would answer that question. It's in units of pain and not necessarily units of like a value, because I've been on the phone with people that are upset or worked up over their wastewater plant getting 50% more volume during a rain event, and then I'll pick up the phone and be on somebody that where it goes 10x. And in fact, like that first example I had was a 10x instantaneous value. So, but I would say generally speaking, at a wastewater plant, if the plant daily volume is going 3x and 4x, that's kind of a, if I had to just kind of the center part of the bell curve, that'd probably be it.
Thanks, Mike.
3x or 4x.
Great. Um, Another one was what cost or time considerations should be used to determine where to start locating I&I?
Yeah, so the general approach, for me and speaking with people often, it's marrying up an available budget with kind of the pain, so to speak. So, um, some utilities I would say most have a pretty good idea of like, hey, they very few utilities have no idea where the I&I is. Like they can generally pare it down to a third or a half or two-thirds of their system. So, that would be the starting point, eliminating some and just starting out with a couple of data points to further reduce the area down. And then once it's reduced to a certain point, then applying more resources. And generally all of that could happen within 12 months, right? So you're not going to get the annual groundwater infiltration differences, but for I&I purposes, like, less than 1 year. And look, at the end of the day, we've had it happen before. You put equipment in, you're at the end of a dry cycle, the equipment's in the ground. 1 week later, rain event. I mean, that's only one rain event, but the cat's kind of out of the bag very quickly in that case. So we do lots of 3 and 4 month studies. That's what we see a lot of. So hopefully that helps.
Great. I think, Mike, appreciate your time. Unfortunately, for all the participants, we're running out of time to be able to open it up for questions. But we do want to reassure you, though, that if you do have some questions, you will be getting subsequent follow-ups from us with information on presentation, as well as the ability to access the recorded version of the presentation, and also the ability to ask any questions after the fact that you thought of, and we'll answer those as best we possibly can. But looking forward to helping you find and locate I&I and putting a strategy in place to help you, save some money and make your folks more focused on on the key things that you're working on within your utility. So thank you everyone for your time and have a great day.